been drawing here, we have a rotation around this around this axis. We are rotating here. This is denoted by this joint. We can start numerating the joints. We know this is 0, 1, 2. And here we have the n effector, and of course, we go from 0 to n-1 because we have n equal to 3. This is the number of degrees of freedom we have. Okay, next, we're gonna start by selecting the zeta 0 axis, which is this. I'm struggling for the drawing, but this is gonna be the zeta 0 axis. Okay, this is zeta 0, and of course we can find the other axes here. From here to here, this is gonna be zeta 1. This is gonna be zeta 2. And at the time we find we're gonna create a parallel frame with respect to the previous one for the n effector. And of course, this is zeta 1, zeta 2, and zeta 3 in accordance to the first step. We're doing well. We're doing some steps here which are straightforward. Okay, here we have that zeta 0 denotes a rotation around this axis. We're gonna denote this rotation as Q1. We have a rotation here, which is Q2. We have a rotation here, which is Q3, and this is the last motor in the system. Which probably the last actuator. Okay, next is locating the origin in any point of zeta 0. Zeta 0 is all this line from -infinity to infinity. But here we're going to create it, the origin in the center of the cylinder in the floor. Okay, here we also can observe that all these three are parallel. Then the common normal is going to be this line. Then all the axes, the x-axes are going to be located along this line. And therefore we can choose conveniently the x-axis in this direction. We can choose x-axis here. And this is going to be x0 axis. And of course, we use the right-hand rule. We point the fingers of the right hand along the zeta axis, and then we curl the finger from zeta to x, and then we are obtaining the y-axis. We're not going to denote the y-axis here because it's not used for obtaining the Denavit-Hardenberg parameters. Okay, next is finding the other x1 is going to be directed from in the common normal from this and this, but these two intersect. Then the next x the next x cannot be along this direction because it should be normal, and cannot be in this direction. Then the only choice we have is in this line or in this line, and of course we're going to choose in this line, because every time we have several options, we usually look for the simplest possible solution. Okay, here we have x1 here. Okay, in the next, we have the zeta 1 and zeta 2 are parallel, and they have infinite possibilities for the common normals. But we're going to choose the only one which lives in the plane, which is contained in which is contained these two joints for the robot. I mean, let me choose the line having this is a straight line here. Okay, and this is going to be x2, and of course this is going to be x3. In the case of the n effector, we have a lot of freedom, but again, I repeat, we're going to choose the simplest possible solution. Okay, now I believe we are ready to start computing the Navier-Hartenberg parameters in accordance to their meaning. There are several interpretations for them. But, okay, these are 4 parameters. Okay, then, yeah, we're going to create here the table. Yeah, here. Okay, and here we have 3 links. Okay, here we go. Then here we're going to have the link number. And here the parameter. And we start with A, D, alpha, and theta. Remember, this is distance along X, distance along C, distance angle about X, angle about C. This and this should be constant because all the motions are every time along the current C axis. But in this case, we have only joints of revolution, revolute joints, then this is going to be the only variable. Okay, we start with the first. Here, it's possible to see that. Yeah, we find A. A is going to be the distance from the intersection, the distance from, yeah, O1. Let me choose this color. Yeah, O1. Okay, it's the distance from O1 to the intersection between X1 and theta 0, but the intersection is in the same point. Therefore, this distance is going to be 0. Otherwise, to find this is like the distance between O0 and O1, this vector, but the component of the vector O0 and 1, but the component along the X1 axis. Like, what is the separation of this along the X1 axis? And of course, these two quantities, these two vectorial entities, sorry, are separated in the C axis, not in the X axis. Yeah, for that reason. But of course, the best is using the procedure, the recipe we have in our presentation. I mean, again, the intersection of X1 with respect to theta 0, and we find the point and we measure the distance with respect to the current origin, which is the same point, then the distance is 0. The distance directed along X1. Okay, next, we are to find the distance along the C axis, distance from this and this. But the algorithm says is the intersection again from X1 to theta 1, which is again this point, the origin of the number I, the number 1 reference frame with respect to the previous one. But the distance should be directed along the previous axis, which is theta 0. Again, the intersection of this and this, the distance with respect to the previous, which is this. Okay, and then we can denote this as L1. This distance, is going to be L1. Easy, isn't it? Okay, next is the angle we need to rotate theta 0 about X1 in order to obtain theta 1, to align these two. Yeah, of course, that we're going to do is extending theta 0. We're extending the vector here, all these, and here we have P divided by 2 is the angle of rotation, pi divided by 2. And we have here pi divided by 2. Okay, let me erase this. Okay, pi divided by 2. Okay, and finally, we need the angle we are required to rotate about theta 0 such that X1 and X0 are aligned. And of course, the angle seems to be 0, but of course, we have here that Q1 is a variable, then the robot is usually this. We have the cylinder here. But if we rotate, we're gonna have X0 here, and X1 pointing with respect to other, inside the page. Okay, then the magnitude of the angular separation is gonna be the same. It's gonna be exactly the same that the rotation of the motor placed here in zeta 0. Okay. Okay, the next steps are far more easy, are very easy. Here we have that A, and here we have 1, 2, 3. Okay, A here is when we are now with respect to the computing with respect to the second joint. Then is the distance of X2 intersecting zeta 1, which is this is the point, to the distance from this intersection, which is O1. This is X2 with respect to the previous zeta here. From the distance from these two, the origin O2. And here is a constant distance, which is going to be L2. Okay, then D is the distance along zeta 1 from the intersection of X2 with respect to zeta 1, which is here. Then is the distance from the previous origin, which is O1 with respect to the intersection of X2 and zeta 1, which is again O1. And as in the previous case, the distance is going to be 0 if the point is the same. Okay, alpha is the angle we need to rotate about X2 such that zeta 2 and zeta 1 are aligned or are parallel. And this is going to be 0 because both are actually parallel. And the next is, of course, the angle we need to rotate about zeta 1 such that X1 and X2 are aligned. But if we rotate about zeta 1, zeta 1 is fixed with respect to this link, then the only is going to rotate is going to be the mechanism is going to rotate about, but this reference is rotating with this link, which is this, but this is maintained, is fixed, is the same. Therefore, the distance is going to be Q2, the angular distance. Okay, this is Q1, but this seems to be, this is Q1. Okay, Q1, this is Q2. And finally, we know we have the same type of rotation. Therefore, the table is going to be then the following 4 parameters are going to be very, very similar. We have the distance L3, which is going to be here because we have the same type of rotation. You are, of course, encouraged to demonstrate this by using the algorithm provided in the lecture. Here, D is going to be 0, alpha 0, and theta is going to be Q3. Okay, and these are the parameters. Please keep in mind these parameters because we're going to use the MATLAB resource in the next video in order to find the forward kinematics. Thanks for watching, and Guillem.